Yes, thank you. And thank you very much for inviting me here. So that's my first time here, so I'm a newcomer compared to the talk you had before. So I would like to tell you a little bit about what we do, which is finding black holes with lasers. So I found this fantastic image, but this is obviously not how we do it. Does anybody know what this image shows? What kind of laser you see here? It's a red laser, yes, but what it is for. So what's the purpose of shooting this laser into the sky here? Say again?
To tell you where you're pointing the telescope.
Nope. Okay, I should have brought my Astronomy 101 talk as well. So this is not what I will tell you about, but this is a guide star laser. You probably have heard about this. So you shoot an artificial star into the sky to help an adaptive optic system to calculate away distortions. So this is an ordinary telescope sitting somewhere there, but it wants to have some defined point in the sky that it knows where it is and how it looks like to calculate away distortions. So yeah, you heard astronomy already, so my talk will be about astronomy. And I think you know how astronomy looks like, people getting their telescopes out, and then you look at the stars, no? That's astronomy. Yeah, kind of, but actually, if you do astronomy nowadays, it looks a little bit different. So this is just one example. Again, something you heard of, maybe SKA is a big telescope project that's just been started where the UK is involved in, but it will be located in South Africa and or Australia. And these are just 2 or 3 or 4 test antennas. So this will be a huge array of antennas looking like this, radio telescopes. So seeing not optical in terms of normal camera waves, but radio waves and making images from it. But the point is, they're huge machines, and the actual observer sits somewhere else at a computer, so probably here in the UK. And that is what we call big science, very much like the particle accelerators. You need a lot of people, a lot of machines, and then you sit somewhere in a computer pressing buttons. And I would like to tell you about another big machine where people sit elsewhere and pressing buttons, doing astronomy, and of which you probably have not heard before. And this is one of these. This particular one is called LIGO. And that's an acronym, stands for LIGO, Laser Interferometer Gravitational Wave Observatory. So the actual title of my talk should be gravitational waves. So I would like to tell you about what gravitational waves are and how we detect them and why we do this, when we do this. But actually I will tell this as a little bit of a personal story, so a little bit how I worked in this field as a student, how I work there now, and what my students do, so that I hope I can tell you 2 things at the end, that this big science is a very slow process. So you can't just have everything, invented by a genius into 2 years and then everything is there. But actually, as a physics student, you can have a big impact on what's happening already. So it's probably the things I find the most surprising myself, and I know that most students don't understand this before, that you can have an impact, but it takes 30 years. Okay, that will be my story. So let's start with gravitational waves. So most people have not heard of those things. So what are gravitational waves? The reason we want to look for them looks like this. And this is how the university mostly looks like. Do you know what I mean by that? 96% of the universe is dark. So we know from measurements that there is stuff out there, and we can see some of it, stars and some planets and so on. But we know that from the energy and mass we can kind of assume in the universe to make everything look as it should look like, we know that 96% of the universe is dark, meaning we can't see it. And the only way we typically see things is by looking with a telescope. So if it's dark, we can't see it, we don't know actually what it is. So that is the reason we want to try to measure something else. One of these something else's is called gravitational waves. And here's just a kind of buzzword summary I usually give in a science seminar. So what are gravitational waves? I will explain this all in a few slides afterwards. So first of all, they are predictions. So that's a theory. Somebody had an idea that these things should exist. And the someone was Einstein when he wrote his theory for gravity. And out came gravitation waves as one of these predictions. And then what this actually kind of means, you try to make a picture of it, and the picture we come up with is those are ripples in space and time. The other thing is we want to do astronomy with it, so what produces these ripples in space and time? Well, heavy objects that are accelerated. So you need a lot of mass, and they'll have to move very quickly. So that could be, for example, black holes or other cosmological objects. And yeah, so this is all a little bit complicated. Let's try to see whether we can explain this a bit better. So this is a photo of how we try to explain it during our outreach session and so on, where the idea of space and time, of something that can stretch and that can have ripples, is a little bit visualized. So the idea to understand it is to see space and time as a rubber sheet, where the curvature in this rubber sheet gives you gravity. Okay, step back a little. You know, gravity is usually a force, so Newton's law of gravity, two masses attract each other. And Einstein tried to calculate that a little bit more precisely because there are some things that didn't work. So planetary motions, for example, are not exactly following Newton's laws. And there were lots of people trying to get this all together. And Einstein at some point had the idea to write down these equations slightly differently. The idea he had was to not have these kind of forces between masses to be instantaneous, but that they were also limited by the speed of light. And to write this down in a nice, elegant way, he had this tensor algebra, and that effectively transformed the force into a curvature of space-time. So the way it works, you have a mass, you put it somewhere, and it curves space-time. And the curvature, again, attracts the next mass. So gravity is curvature. So mass creates curvature, curvature attracts the other mass. And this is how we demonstrate it. So you put a heavy object in the middle that forms this kind of shape. So that is a gravity field. And then you take a smaller mass and you roll it along, and it forms an orbit automatically. So you can imagine this is not attracted by gravity. It's just the shape of this rubber sheet that forms this motion. So just trust me, this is so far the best theory on gravity we have. And if that is right, so if you have this elastic rubber sheet and you move masses, and you can see this, if you actually do this with this demonstrator we have, you see there are ripples running through the surface. So everything that is elastic and does that should have ripples. And that's the same that came out of the equations of Einstein. He said, oops, if I do this, I get waves. And these waves are really just changes of the gravitational field or space and time together. Okay, so let's assume these exist. Where do I get those from? As I said, accelerated masses. So if I make this, I'm accelerating my arm, and I'm creating gravitational waves. So everything around us all the time generates these gravitational waves. But there's a slight problem with it, that the energy that you create the gravitational wave with depends on the mass that you're accelerating. And here are just two examples. So there's a claw, one of these big things in an amusement park in Australia. And below I've written the luminosity. So that's one of these units. It's like a light bulb, you give it in watts, so how much radiation is coming out of that thing. And you see it's a 0 with, can't remember how many zeros, and then a 1. So it's a very, very low energy light bulb in terms of gravitational waves. When you go, on the other hand, to something like two black holes that orbit around each other, then you get, again, a very, very many zeros, but all in front of the dot. So this is a very, very high luminosity source for gravitational waves. And while you can do the math, and you can see that everything we can do, like with the claw or anything we move on Earth, is too weak for us to see. But there are things out there in the galaxy, in other galaxies in the universe, that are very, very heavy. So they make these very luminous sources. And that's what we hope we can see. And that's why I'm talking about astronomy. Because there's nothing on this planet that we can possibly see with gravitational waves. That's why we have to go elsewhere. But elsewhere, there are quite a few sources that normal astronomy has found already, and we know they exist. So there are, for example, binary systems. So probably you don't know this, but most of the objects in the sky like to exist as a binary. So stars that you see, but also kind of bigger system, like to end up in a binary form, which is kind of the natural behavior. If you throw a lot of things together that orbit each other and have a chaotic system and they kind of organize themselves like our solar system did, on a star level, a lot of this self-organization leads to binaries. And if you have binary stars, then you also expect to have binary black holes and binary neutron stars and binary white dwarfs, everything in double. And these kind of spin around each other, and at some point they orbit around each other closer and become very violent systems. The other thing that you heard about is supernovas, which are just star explosions, but of course it also means there are great masses accelerated. So we know these exist, and we detect them with normal telescopes, so we expect that these would also generate gravitational waves. Then there are some other things that we know exist, we don't understand so well exactly, like pulsars. Pulsars are neutron stars that rotate very, very quickly, and we see them as radio blips in the radio antennas that I've shown you before. But we expect them also, because they rotate very quickly and not being exactly round, to be accelerating masses, because they rotate very quickly, and generate gravitational waves. And the same for accreting stars, where mass, a lot of stars have a companion, where the mass from the companion is falling onto the other star. It's called accretion. So this process should also be moving a lot of mass very quickly. So there are a lot of these things we would like to know more about, and maybe gravitational wave can show us more. So this is a simulation we then done in a computer. So imagine you have two, let's say, black holes that orbit each other, and you visualize the gravitational field lines as these kind of green things. And as these become closer and spiral closer together, they start to rip each other apart and finally form one merged black hole. And during this violent process, the gravitational field gets very strong and radiates away in these red fields. So what you get from that is effectively there's, at the end of a long process, some violent, death spiral at the end that generates a lot of gravitational field that radiates away. And this is something we would like to see. Now, just another simulation that looks a little bit further out. So again, this big blob is where it's simulated. Just in the center is now something like these two black holes that rotate around each other, and the big blob is just the simulated gravitational wave field. And there's somewhere on the left, there's this little tiny yellow ball swimming in there. That should be us, somewhere far away. So this is galaxy scales. So at our position on a planet somewhere else, this would hit us later, obviously, and at that time it becomes this ripple in space and time. So it's really like a water wave hitting you when you're sitting somewhere else. So somebody throwing a big rock in the water here, and you're in a boat there. After a while, your boat slowly rocks, and this is all we can see. So we're not looking for something we can make a picture of. It's more like a microphone or like bobbing a cork in the water. So the thing that we can see is these kind of echoes of a distortion in space and time somewhere else. Sounds very weird, but this is how it would sound like in real. So if somebody asks you how gravitational wave sounds like, you have to make whoop. You know where this whoop comes from? So that's one particular example. There are many very, very different versions, but this is the most common one and relates to the pictures I've shown you before. Anybody have an idea why the sound is like you heard just now? Well, it starts low. Well, it has this kind of stuttering as well, but I'm talking about that as low and then it going to higher. Whoop. You know why that is?
The wavelength change.
Yes, and Any idea why that is? These things get faster and faster. So what you hear is really the rotational period of something that's spinning. So this was the signal for two neutron stars or black holes in spiraling. So they start doing this slower, and the closer they get, the quicker the orbit becomes. And that's why the wavelength, which is just proportional to the orbital speed, goes quicker. So this would be our astronomy. So no pretty picture, but a lot of sound. So there's a whole department everywhere of people trying to make then nice images out of sound. It works similar to sonar. You need microphone technology just applied to astronomy, but that's not what I would like to talk to you about. There's another thing that we can do with gravitational waves, and this is to help people like at the Sky and Telescope magazine to finally understand whether Einstein was right or was he wrong, because what we want to do is to measure a prediction of the general relativity that Einstein proposed. And even though we think this is a very good theory, it's a theory. That means at some point it will be wrong. So Newton is still right when I drop an apple here, but he is wrong when I want to compute the planetary motion of Mercury. So Einstein is right when I want to compute the planetary motion of Mercury, but is he right if I want to compute two spiraling black holes? We don't know. We haven't done it yet. So that is something, again, where a lot of people are interested in. And again, that's not something I'm going to tell you more about. What I want to talk to you about is the detection process. So I'm an experimentalist, and I'm working on the instrument. So I'm building the machines for detecting these ripples in space-time on Earth. And that's what I would like to tell you more about. So what we use to detect gravitational waves is laser interferometers. And to show you how that works, I have to leave this fancy presentation and show you some little programs that my students have written to explain this a little bit better. So the first thing is, what does actually a gravitational wave do when it hits us? But what we can actually see is that it changes the length. So this is a typical example how we try to explain it. These balls there, these red circles, should be free-floating masses somewhere in space. And then there's a gravitational wave passing through the screen like this. And while it does this, it would stretch and squash the length between these three masses. So if you could put these somewhere in space and a gravitational wave would go through, you would see something like this. And as I said, gravitational waves are everywhere all the time. So you can, if we can get some light into the audience, that works a little bit better. So the gravitational wave that's coming out of the screen hitting you would then stretch and squash you all the time a little bit. The only problem is here this effect is very exaggerated. So unfortunately this is so small that we can't see it, but it happens all the time. And this is what we want to detect. So if you want to detect something like this, what you can do is measure length. So what I wanted to show you is that these, how this actually, what is shown here in the top row actually works in real time. So we're talking about these kind of frequencies. So things are moving as you see them. The only problem is that it's very small. So what we want to see is what I call their delta L, as a change in a length, L. So let's say I have a meter, then I want to see how the meter changes when the gravitational wave happens, and I have to multiply that by the amplitude of the gravitational wave, which we call h. And the problem is written there, h is tiny. So it's 10 to the minus 22 for an optimistic expectation. So if we have 1 meter, it would change by 10 to the minus 22 meter. Does anyone of you remember how large an atom typically is? Shout louder. Minus 9? No, smaller. 16 is good. I usually remember 15, depends on the atom. So this is a million times smaller than an atom. That's what we want to measure. And that's why the detection, I mean, the experimental building an apparatus that can see that is fascinating and complicated. So the way to do this is use laser interferometry. That is something we have as the best instrument, and it's quite old. So without a laser, it was invented 1887 by somebody called Michelson, and this is how somebody recreated that. It was done with an oil lamp, instead of a laser, but it works the same way. So you have two interferometer arms. I should probably show you that sketch again. So the lower one shows you an interferometer. So you have a light source on the left, and then you split the light into two arms, and then it comes back and overlaps again. And because light is a wave that can interfere with each other, depending on how long the travel time along these arms was, the output, which is in the, this way, sees a bright or a dark spot. So you just look into it, and it is bright or dark. And this changes when you change one arm length. And if you change it by one wavelength, it goes from bright to dark, and that's what we call a fringe. So you can sit there, and when you see it going from bright to dark, you see, the arm has changed by one wavelength, which is a small number. So for normal light, let's say 10 to the minus 7 meters. So that's not quite as good as we want, but it's not too bad. So, and then you can try to look better than just dark bright. You see kind of changes in the brightness. And Michelson looked there with his eye into the interferometer and tried to do that. And he thought he could do this to a % level change between dark and bright. That's what we call a % of a fringe. Now, we got a bit better, mostly because of the invention of the laser. So with a laser, you have a very, very stable light source where you can detect gradual changes in brightness much, much better. And this is a report for a ready gravitational wave detector, but effectively it's the same thing. So the laser is here on the right, and then you have these two arms, and you detect the output, same method, just better technology. And that is 1972, just after the invention of the laser. And you see the detection was much, much more precise, so 1 million times better already. And since then, we even got better. So we have now, again, the picture of LIGO, one of these big things. And now you probably recognize a little bit more what this is. So this is two very long tubes with a corner. So this is still the L shape of the Michelson interferometer, and there are laser beams traveling around these tubes, and what they do is measure length. And precision now has even more zeros, and here we finally can see length changes that are smaller than that of an atom, and even smaller than of an atomic nucleus. So these things exist, and there's not just a LIGO detector. So LIGO even has two. Remember, I told you we only hear the sound like a cork bobbing on water. So it's like a submarine hearing a different submarine. If you want to know where that other guy is, you have to have a couple of microphones and then do this triangulation exercise to see where the sound came from. And we have to do the same thing. So if we have only one antenna, we can detect it, but we don't know where it comes from, which for astronomy doesn't help us very much. So we have to have a network. So there are a couple of these things. So the LIGO detectors too, then one in Italy, Virgo, one in Germany is called GEO. There's one under construction in Japan and one planned for India. And these are ground-based, they're also space projects, which I will not talk about. So I would like to talk to you about these projects and show you a little bit how they evolved and where I worked on these, so that you get a little bit of an insight how it is to work on a big science project. And what I like about our science is it's new. So particle physics, we heard before, was at this stage 1960. Okay? So even though for you it might be new that there is a Large Hadron Collider, they had already big accelerators and nice results and won Nobel Prizes 40 years ago. So we haven't. Okay, so we're just starting. And you can be part of this by seeing this in the news, by looking this up. So this will be kind of the stuff that is old news in 40 years, but now it's pretty fringe science. So the first generation of detectors tried to build these type of Michelson, just much better. And there were a couple of projects, so I'll give you some of these names already. And the key here is the time. So they were proposed in the 80s because with a laser we thought, well, we can maybe do it. Then between the proposal and actually the building, you actually then get to work and try to invent the technologies you need to actually do it. Then somebody gives you the money and you start building. That was in the 90s, and you say, I better work harder on the new technologies now because I really have to make it work. And while you're building, you're still inventing stuff to build it in. And then in 2000-something, we were ready and stopped working on it and switched them into science mode. That means everybody hands off and just try to detect something, because while you're working on them, they can't see anything. So that was what we call the first generation of detectors, and I worked on these. So I'll show you a few pictures of those to get a feeling for it. So this is the German one, which is actually a German-British version, so half of it done by German groups, half of it by groups in Britain. And this is where I did my PhD. So I was sitting in these containers there, so not as fancy as you might hope. Inside it looks a little bit fancier because it needs to be all clean. So these are typical vacuum tanks like this guy, just a bit bigger and better, because we need vacuum for the laser beam, otherwise the air or gas would distort our reading. And as I said, we have new technology, so I show just one example for the various bits and bobs that go in there. So what Geo pioneered at that time was the so-called mirror suspension system. So when you want to measure length change for a laser beam, what you have to do is you send the laser beam and then you bounce it off a mirror so that it comes back. So then the motion of this mirror is effectively what you want to see. And you can imagine if you want to see it to 10 to the minus 18, 20 meter, that mirror has to be pretty damn quiet and good. And this is to make it quiet. So the mirror is this lower circle, which is the lower piece of glass on this photo. And all above is the so-called suspension system. And that's like in your car where you have a spring so that when you drive through a pothole, the shock wave doesn't travel to you, but is kind of suppressed by something which is oscillating, a spring. So we have springs up there as well, but we have also pendula, so just wires, but they all do the same thing. If something shakes on the top, the mirror doesn't shake. Okay, so that's the suspension system. And of course, the details are quite complicated, so there's a lot of development going in so that this thing is really, really quiet down there and doesn't move. So as I said, what we actually then do, we sit in a computer room and press buttons. So that was me in 2001, and you see we were terribly understaffed, so I had to clone myself to be there at least 4 times, and I had a little bit of help from Einstein as well sometimes. So that was our control room to control the interferometer in the early days. So after my PhD, I moved on and worked in Italy, and their detector is called Virgo, which is near Pisa, and this looks a little bit more fun because the landscape is nicer and it's longer. So this one is a 3-kilometer one, and you see the buildings are a little bit bigger, so they had more money to build it. And one of the things they spent the money on was, again, the mirrors, but on a different thing. So, okay, we now know how to suspend those that they're quiet, but imagine we want to measure light bouncing off a surface and then how the surface moves by 10 to the minus 20 meters. But even one atom peeking out is much, much larger than we want to measure. So you can imagine that the surface must be very, very smooth, and then also the quality of the material must be very pure. And so this is a mirror, even though it looks like a piece of glass, because it's made to be reflecting only for that particular laser light that we want to bounce off. So for normal light, it looks like a piece of glass. But we wanted to buy these things, and they weren't available. So we had to pay several million euros to a glass company in Germany to make us better glass. So now it's sold by the company also to other people, but at that time there was no market, so they wouldn't do it otherwise. And then they need the scientists' help to actually understand what exactly we need. So this is what the biggest impact of Virgo was at that time. So when I went there, these glass pieces were just delivered and then installed. And then one of the tasks that I worked on was actually, you have a 3-kilometer long tube, and it's this big, and you have a laser beam, and you want to shine it in so that it hits the end of the tube as well, which is actually not so easy. So that took us some time, and when we finally done that, just a tiny step in the whole process, everybody was very happy. So that's, again, me. You see, the most interesting thing, I didn't change my top from going to Geo to Virgo 2 years. So that was the control room in Virgo, and that's really, again, how to work. So the laser is somewhere else, the mirror is somewhere else, but because it is also sensitive to movement and to noise, you have to be somewhere else, and everything is computer controlled. So we did all this work from that control room when we had things working, and then if things stopped to work, we went into the lab and fiddled with this. This is the kind of experimentalist work I've done there. And then the biggest detector in terms of the length, but also because it's the most advanced one, is LIGO. But I will not tell you very much about this because there's the LIGO magazine, which is really something you can download and read and find out a lot. I think that's the best thing out there at the moment to find out what's going on. And I'm saying this because that's me again. I'm the editor-in-chief of that magazine. Why I tell you this is that this is a typical thing you do as a scientist. So I'm a researcher. I want to be in a lab. So why am I here, and why do I do this? So we kind of have various roles, and we're expected to have various roles. So I'm expected to do outreach. I'm expected to do so-called service work as well for the collaboration. When you are in these detector groups where there are 1,000 people working on something, everybody has to help to make it work. And one of the jobs I took to do my service is this editor-in-chief of the magazine. So that's downloadable, it's for free, easy to Google, so you can do that later. And, well, we haven't detected anything yet. Okay, that didn't work. So we learned a lot in the process, and we built this huge collaboration. As I said, this is like CERN was in the 60s. The main work is to get things going, to get a momentum, to get people on board that this is interesting and so on. So we built all these detectors, we measured for 10 years, and we didn't see anything. So what do? Of course, we built another detector. And that is, of course, bigger and better, and that should then finally work. And I think actually will, because we learned so much, we've become now an international collaboration of the order of CERN in terms of how much money is spent there, how many groups are participating. So this is not fringe science anymore, even though it hasn't reached yet the public, it is now a big science as we wanted it to be. And what do we do by making it better? So we take the existing sites, which were the expensive part, to build all these big holes and big tubes, and replace some parts with newer parts because we understand better what we want to do. And this is going on now and will be still looking like this until 2015 before we can again switch it on to take some data. And advanced here is a strange keyword for better. But what I mean by that is we have still the idea of the microsm. We throw more optics at it. And this is for making a couple of noise couplings where something is shaking, and because of that our mirrors are shaking, and because of that we cannot see the gravitational waves. These kind of couplings lower by making the system more complicated. But by understanding more, we can do that now. So I'll just give you one example. When this kind of little symbol at the bottom there is showing you a photodetector that looks into this fringe, seeing whether it's dark or bright. So I draw this there as this kind of official symbol for photodetector, but when you look at this, how it's looking in real, this is this table on the right, which is 1 by 2 meter. And the reason why it's so complicated is because you need to detect high power beam, very sensitive, and you have to detect various degrees of freedom, also how it moves and how the shape changes. And for that, you have to split it in various components and have very specialized detectors. So this is a type of advancement we now understand and we can do. So the inside of one of these vacuum tanks looks also more like a building now. So again, this is something like this, but people working inside. Of course, no vacuum at that time. So they work and then they go out and then you pump down. But what you see there is this kind of suspension system so this kind of shimmery thing in the middle. So not the one with the green spot on it, but the one below is one of the mirrors. And this is the key, so one of the hard component of the system that keeps the mirror quiet. And we've built in Birmingham and in Glasgow here in the UK part of that system. Most of the system is actually from the UK. And in Birmingham we've built just one control component for it. And this is one of the famous guys we sometimes then get into our lab. So that's David Willits visiting our lab in Birmingham. And like you, he was probably surprised that it's actually students or PhD students that built this hardware that's then shipped to the US to be installed in this multi-million-dollar machine. So if you're a student, PhD student, you would actually have your hands on these things. So that's what we've done. And so then hopefully in, let's say, 2016, we detect a gravitational wave. Somebody will get invited to Stockholm, will get a Nobel Prize, and the astronomy will start. So this, for sure, will be like the Higgs detection just recently. So there will be a big media attention, and there will be astronomy finally done. But I'm an experimentalist. I build detectors. So the question is, what do I do then now when advanced LIGO is finished? So, of course, we don't stop. We go on. And there are two things I want to show you quickly. So the one is what's going on between now. So we built all the parts. They're all shipped to the US. what do we do? So the problem is once you install these things in a very complex machine and switch on, nothing will work. Because individually they work, but if you put them together, they don't. So there's a phase that's called commissioning, where you try to make it work. And just 2 weeks ago was at this workshop, commissioning a simulation at the LIGO site, where we try to understand in advance, so before we try to switch it on, why it will not work. And then to try to already devise some strategies how to make it work. So one example, what could go wrong? So long vacuum tube with a laser beam. At the end of these tubes, you have these tanks, guys like this, bigger. In each of these tanks, you have this kind of suspension system in which there sits a mirror. Okay? So actually, I didn't tell you that in detail, but there sit two at the end of each arm. So you basically create a resonator between these two mirrors. Now, this is one of these mirrors, 40-kilogram glass piece, very expensive, very clean, very flat. But how flat? So on the right, you see here a surface measurement of that mirror. So we've delivered, the company we ordered these mirrors from for LIGO have delivered. And now the question is, can we accept them? Do we sign the check for a couple of $1 million and say, yeah, thank you? Or do we say, no, that's not good enough? So we do a lot of work on metrology where we just measure the surface. And you see the scale probably not, but this color scale is plus minus 2 nanometers. So the surface is not perfectly flat, but the highest and deepest valley is just a few nanometers. So the question is whether it's good enough for us or not. So how do we do this? We do optical simulations where we take the measurement, put it in a computer, simulate this kind of thing where you have two mirrors. And then what I've done here, so what you see as a video is a simulation where I just move one of the mirrors. And then you see various kind of shapes appearing. What we want to have is this kind of bright round shape, which is the usual laser beam. And the other shapes are created by these distortions. And by using the simulation, we can kind of anticipate what we will see in the experiment. And first of all, just make the conclusion, is this good enough or not? So this work was done last week by one of my students in the LIGO site. Again, PhD student making the decision whether we accept these several $1 million mirrors or not. And what we used for that, and that's another funny story, is the simulation I wrote as a fun project when I was a PhD student. So that was something I was not supposed to do, but I was kind of liking programming, even though I was an experimentalist, so I did this on the side because I wanted to play with optics in the computer. And this is still used, so this is on this website as an open source project. It's not somewhere secretly hidden for this big project. It's something you can download and play with it. And again, it shows you how close you can get to big projects easily. And just to give you an example for the real life, so we do the simulation so that we know what the interferometer will do to us, so that it smiles at us rather than laughs at us. So this is actually a reflected laser beam that should look like a normal round spot, but because of the surface diffraction, it has strange shapes. And this was one of the first cavities that was installed in advanced LIGO. It had this kind of shape looking back at us. Okay, so the other thing I wanted to show you is another thing I work on, which is called optical design, which is a little bit less experimental, where we just sit down and try to understand, okay, what we've done with LIGO, advanced LIGO, can we do this still better? And we would like to do something in Europe, and that's what we called Einstein telescope. The idea is to be, again, bigger and better and go underground. Again, a little bit like CERN, we go underground because it's more quiet. So this idea is that you have a triangular shape with several detectors underground as a facility like CERN that lives for 50 years. And we have to come up with what we should build in there. So this triangular shape here like this just is tunnels. Nothing in yet there. And in there, we have to build interferometers again. And just the tunnel size is enormous. So if you look at the end station here, where all these tunnels come together, this little dot there is a person. So this is expensive, and you have to get it right. And we have this same structure as before, where there's vacuum tanks that got bigger. There are vacuum tubes connecting these things. But the key, of course, is how to arrange them such that they are cost efficient. So that's a little bit different work from my usual optics, but it's interesting. So it's more project management, where I try to squeeze them into each other so that they cost less. But still, you then, of course, have to make very sensitive interferometers, so that there's a kind of work that you have to do. You can't hand it over to a tunnel engineer because he wouldn't know what the interferometry needs. So you can find, again, on the same web page, an interactive graphic where you can actually see all the optics. So this is a zoomable picture where you see all these mirrors in the Einstein telescope. And why, again, I think is a good example is this triangular shape, the way the interferometers are aligned in this very big European project are all based on papers that are written by my students. Not only mine, but let's say 10 people, and 2 of them were in Birmingham, 2 of them were in Glasgow, 2 of them were in Hanover, and these people will define the shape of something which is going to be built, hopefully, in 20 years somewhere in Europe underground. So this is kind of what I call a high impact of your sitting down at desk and thinking work you can do. So that's more or less close to the end. I hope I have got 2 messages across. Science is a slow process. So sometimes that's not so clear when you see these big things that we are actually needing years and decades and another decade to get from A to B. But that is how it is. It can't be rushed. But in all these big projects or smaller projects, if you are a PhD student, you can have a big impact. And your work will really define the shape of huge machines somewhere on the planet and what we detect with them. And with that, I would like to thank you. And all this stuff you've seen, the kind of crashed demonstration, the simulations I wrote, something about gravitational waves you find on this webpage. So if you have questions afterwards, please go there or contact me. Thank you very much.